Okay, so welcome everyone. So it's a pleasure to have Ansuman Banerjee from ISI Kolkata to have here. So Ansuman has been working on formal methods in various application areas of formal methods for like several years now. And today he's going to talk about bounded model checking and application of learning in formal verification. Yeah, over to you, Ansuman. Thanks.
Thanks, Ashish, for inviting me and hosting this talk. It's really a pleasure for me to speak about our recent work and share the results that we had. So this is joint work with Devina, our postdoc, Shumona, a young colleague of mine, and Raj, who is a scientist at IBM Systems. So in this work, what I'm going to talk about is a very recent experience that we had. So this was a problem that came from the colleagues at IBM. So they said that they have a very nice formal verification tool called SixSense that works for edges, has been the principal tool for certifying IBM processor designs. Now, they wanted to collaborate with us on what we of a commercial tool. I mean, how does it work? So we asked several academic questions, some of them being, okay, how do you represent transition systems? Is it how it is written in the textbook? How do you write SAT solvers? Is it what we read in textbooks, or it's something beyond? Are there some engineering tricks that also go on, which possibly we don't get to see in the textbooks? What is the secret of the success? How do your tools differ from the academic tools that we use in there? What is the secret key of your scalability? Why can you scale? Why can do IBM tools scale to these big designs, whereas academic tools don't? So then they came up with a very interesting answer, and they said, okay, in this discussion, we want to give you one of our pain points. Well, there are definitely many engineering contributions that drive these tools, which possibly is a choice of clever data structures. It's not really what the algorithms that we read in textbooks then. These are not really the ones that we implement inside. So when we create implementations of standard SAT solvers, standard symbolic packages, when we represent state transition systems, the simple finite state machines that we all work on, there is also a touch of engineering. So when we really write this code, we also think that how it's going to interact with the underlying hardware, how the cache algorithms are going to shape up, and all these other tricks come into the picture. So it's really a big journey that they face. So then they came up with a very interesting problem. They said that, okay, we are happy about the performance of the algorithm that dominates formal verification today, namely bounded model checking, about which I'm going to talk about soon. But there is an interesting phenomena that we are observing. So that's what started this discussion, and that's what I'm going to share with you. It started with a lot of experiments and then trying to conclude what those experiments essentially tell us based on some theory that we already knew from reinforcement learning, and then trying to bridge the gap of making something that works. The happy part of this story is like we finally had a paper. Not only that, the code was actually integrated and with these folks at IBM who were really interested with the results, because we were possibly doing better than the industry. The fact that we could actually bring theory and engineering together on some benchmarks, we were actually doing much better than the industry state of the art, and that's what made us even more happy. So let me begin with a small.
You have to just click on the screen.
When screen froze?
No, just click on the screen with the mouse.
With the mouse.
Yeah, now it should work.
Yeah. So, as you possibly many of you know, formal verification is the de facto verification technique today for hardware and software validation. And what is the key principle? This is how it works. So, typically, you have a system that you want to analyze with respect to a specification, which again is formally specified. And what you typically do is you want to analyze whether there is any trace of the system that essentially gives you a bug, or you can prove convincingly under all input scenarios this system is going to be behaving correctly with respect to the specification. So this is the key principle of formal verification. Now, formal verification exists in different forms today. In fact, there are many formal verification algorithms. in the ED industry, in the electronic design automation industry, the chip design industry, FV algorithms are the standard practice before you go for any chip sign off. So any chip that gets signed off has to have a formal verification run. Typically, there are three competing algorithms that are preferred. One is symbolic model checking, in which what you typically do is you take the system, you extract some kind of a finite state description of the system, and then you represent the state transition system symbolically using decision diagrams, binary decision diagrams, using satisfiability clauses, or some other symbolic form. So that is symbolic model checking. Typically, all the commercial tools that you can think and that you know of, formal verification engines, they have a symbolic model checker, so which essentially invokes this kind of a representation for easier manipulation. The other prevalent technique is property-directed reachability. So this essentially starts from the specification, what you essentially want to prove about the system or what you want to find a bug with respect to, and then it does a property-directed reachability. This is often called PDR, as the name suggests, and this is also quite popular in the industry today. What is going to be of more interest to us today, and that's the key principle of our talk, is this third technology. It's called bounded model checking. And I'll go a bit deeper into how this works, and that's what inspired us to look at this problem. So henceforth, we'll talk about bounded model checking as BMC. So what is the overarching idea? Just think of a simple circuit. It's simple arbitration circuit. So from this circuit, you typically the formal verification algorithm extracts some kind of a finite state descriptions. For simplicity, I take a very simple finite state machine. This is where your journey starts. So what you're essentially interested to analyze is if this system meets certain specification. Now, what is the difference? What is the extra confidence that formal verification algorithms give you? So when a formal verification algorithm certifies that the system is correct, it essentially means that it's correct with respect to any input scenario. So you don't really need to worry about, okay, this input got missed, that input got missed. So this is the exhaustive confidence that formal verification algorithms puts on your plate. So that is why formal verification is so popular today. On the other hand, if there is one scenario which the system does not, under which the system does not satisfy the specification, this formal verification engine will give you that scenario. We call it popularly a counterexample. So these are the two key principles that a formal verification tool typically works. The usual initial step, be it hardware code or software code, is to extract out such kind of a finite state system description from your underlying system. Additionally, what you also have is a formal specification. So let me take a simple example. So maybe for this, the formal specification that the user is interested to verify is whenever this input R1 is high, whenever input R1 is high, the output G1, the grant G1 must be asserted for the next 2 cycles. So what you see here, this is the design that you're going to verify. This is the system to be certified. So these are sequential elements. This is a big AND gate, and these are inverters. So whatever comes up, whatever goes in as R1 comes out as G1 in the next cycle because of this sequential element. So this is a 1 cycle delay. And the specification that the user is interested to understand is no matter what be the value of R1, R2 over time, whenever the signal R1 is high, G1, the grant G1 must be asserted for the next 2 cycles. So a little semi-formally, this English language would mean this property always, that's kind of when R1 is high, G1 must be asserted for the next 2 cycles. So whenever R1 is high, that implies that in the next cycle, you have G1, and the next cycle, you have G1 as well. So this is kind of a semi-formal translation of this English language statement specification. And the task of a formal verification algorithm is to examine if for any value of R1, R2, this specification is violated. So that's the simple illustration of formal verification. In particular, this technique of formal verification called bounded model checking or BMC, what it does is it does this task incrementally. So while on one side, the techniques like symbolic model checking or property-directed reachability, they work on the principle, on an entirely different principle, where they first extract this big state machine, then they represent this specification formally, and then they do some graph theoretical algorithms to find out if this indeed falls on this. What bounded model checking does is it incrementally unrolls the state transition structure to find violations. And I'll give a concrete animation to show how this works. So the essential idea of a bounded model checker is to represent an unfolding of the state transition system over time and internally create satisfiability instances and invoke a SAT solver. So this SAT solver is the hero of this work, which essentially gave us the key ideas that we did in this work. So let's understand how bounded model checking essentially works. So think of this as your finite state transition system, which you are trying to analyze with respect to this specification. That whenever R1 is high, next of G1 and next G1. G1 will appear. So in terms of this state transition system, how do you read the specification? So what you're essentially saying is, if you are at any of these states, if you're at any of these states and the input R1 comes, the next two states that you go through should have G1. So that's the essential idea. Since the specification said whenever R1 is high, G1 must be asserted for the next two cycles. So you can read this property in terms of this state machine as, if you are in state this one and you see R1 has come, then the next two states that you visit, must be having G1. If you are currently at this state as 0 and R1 comes, then the next two states that you visit must be having G1. That's same for S2 as well. And this is what you want to guarantee always. Now, the way bounded model checking will typically solve this problem is, it will first take this state transition system and it will unroll it over time. So what do I mean by unrolling over time? So let's begin with the start state. So what is this? Yes.
How do I say that G1 is being isolated from that picture?
From this picture, so it's not really shown. The G1, G2s are not really shown. Yeah, so you can't really understand whether this state machine indeed satisfies the property or not. So the inputs are labeling the transitions, but G1, G2s are implicit at these states, S1, S0, S2. So I have not shown the values that will come. Okay. So this picture is just for understanding how this unrolling is done. But if you look at this picture, this is how you will on this circuit. If you just do a small calculation, what you can see is this circuit does not satisfy this property. That is because, just imagine a situation where R1 is 1 at some time point, which means G1 will be 1 at the next time point because of this sequential element. So if R1 is high at some time point, let's say time equal to 1, R1 is high, that essentially means G1 will be high at time point 2. But imagine a situation where R1 is low at the next time point. And if R1 is low at t plus 1, so R1 is high at t, which means G1 will be high at t. But if R1 goes down at t plus 1, then G1 will go down at t plus 2. Which means that if you have a pattern where R1 is 1 followed by 0, this G1 followed for 2 cycles, it's not holding.
Yeah.
So this is what is a bug in this code. And that's what we want to find out using bounded model checking.
And how do you ensure that there should be 3 states?
How did I conclude?
That there should be 3 states.
Oh, that's because we have 2 outputs, G1 and G2. So there can be 4 possible values.
Yeah.
So that's why I have 3 states, because one state was unreachable. So this is just, after that, tuning out the unreachable states. So 2 outputs, G1, G2. So these are what encodes the states, S1, S0, S2. So G1, G2 can be 0, 0, 0, 1, 0, 1, 0, 1, 1. So imagine this is 0, 0, this is 1, 0, this is 1, 1. And the 1, 1 is not a valid state. So the reason I tuned out S1, S2 because G1, G2 cannot be both high together by the virtue of the fact the way they are connected. If you see G1, it's connected by an inverter here. So both simultaneously 1 is not a possibility. So the 3 states that we have are 0, 0, 0, 1, and 1, 0, which gives you S1, S0, and S2.
No, but that also has a delay, right?
Yeah, but in the same cycle, G1 and G2 cannot be high together, right? Because if you have R1 high, then automatically G2 in the next cycle will be going low.
Yeah.
Because there's an inverter. So if R1 is high, and if you have R2 high, it also depends on R1. So that will prune out the 3rd state. So indeed, I should have shown the G1, G2 values here. But how the exercise that we just did in our mind, how the bounded model checking tool going to do this exercise? What it will do is, it will first examine the state machine by unfolding it up to a bounded depth. So it will first look at S1. So this is your S1. What does the property need from S1? Possibly nothing. What it just wants to know whether, if you look at the property, there is no requirement to know whether S1 satisfies G1 or not, because what you're essentially saying that if R1 is high somewhere, then in the next cycle G1 is what you need. So then possibly you'll unroll S0, S1, S2. So from S1, you see there are 3 mixed transitions. You can either go here. So what BMC essentially does is, starting from the initial state, it does an exhaustive unrolling of the system. It will exhaustively unroll the system over time and examine the truth of your property at every depth. So it's kind of a breadth first search that it's doing for a counterexample to the property. So given a property, given a state transition system, what bounded model checking essentially does is it unrolls your system, your state transition system over time, and tries to look for property violations. So when it says that, yes, I found a violation, that essentially means that at some depth, it has found a violation to the property. And when it says that I have not found a violation, that essentially means no state up to this depth has violated the property. So that is the soundness of bounded model checking. That up to the depth that I have examined, I have guaranteed that no state violates the property. So just think of a very simple property. Let's say I just want to know whether X is 0 anywhere in the code. So what if you think of a very simple property that whether X is ever 0, the way bounded model checking is going to work is it will first examine whether X is 0 here. If it has found X 0 here, it's done. If not, it will examine all the 3 possible next states. If it finds X0, which is your violation condition, if it finds X0, X equal to 0 in any of the states, it will say, hey, I've reached a state in depth 1 where X is 0. If not, it will examine all the next states which are possible up to depth 2. And if it gets an X equal to 0 anywhere, it will say, oh, I've got an X equal to 0. And this is what it will continue. So bounded model checking is sound because at up to a depth, it is examining every reachable state in the state transition system. But of course, not complete because it is only bounded up to depth K. But how does this bounded model checking essentially work when you throw at it such a property? So internally, what it does is, so this set of states that you see here, these states are represented as propositional logic formulas. So where do these propositional logic formulas show up from? What it does is, corresponding to each depth, it starts creating new variables. So corresponding to S1, so note that any state is represented by 2 variables, G1 and G2. So any state in my transition system is represented by 2 state variables, G1 and G2. So corresponding to each depth, it starts creating these variables, G1 annotated with the time 0, G2 annotated with the time 0. So this is what represents the initial state. So the initial configuration was given as G1 is low and G2 is high. So that was specified by the designer. So this is a clause. I mean, this is a formula, let me put it that way, that essentially characterizes this state of the system. Then, how does it create this frontier? So how was this frontier created? So this frontier represents your G1, G2 values. So this frontier, you can see here, what is G1? G1 is nothing but the previous value of R1. So G1 at t plus 1 is equal to R1 at t because of a 1 cycle delay here. What is G2 at t plus 1? What is G2 at any point of time? It is the value of the current value of, so G2 at t plus 1 is nothing but R1t negated, R2 at t, and G1t. So G2 at t plus 1 is nothing but R1t bar, G1t bar, and R2. So G2 is the conjunction of these. So G1 is nothing but R1, G1t plus 1 is nothing but R1t, G2t plus 1. So G2 at time point t plus 1 is nothing but R1 at t complemented, G1 at t complemented, and R2 at t. There is 1 cycle delay, therefore that is what shows up in G2t plus 1. So if you represent this, if you take these equations, so this is what you get. So R1 at 0 implies G1 at 1, that's what is the G1 output, and R2 at 0 and not of R1 0 and not of G1 0 implies G2 1. If you unfold this state transition system, so this is the representation, this green one and this blue one is the representation of the finite state machine up to this level. Why do I say up to this level? Because this is your state 0, depth 0, which is characterized by this unique initial state, not G1 0 and G2 0. Note that every state is nothing but a valuation of the GI variables. How do I get these states? I get these states by applying the state transition function. So what does the state transition function tell me? It tells me that G1 at t plus 1 is derived from R1 t. How is the relation derived? R1 0 implies G1 1 and R2 0 and not of R1 0 and not of G1 0 implies G2 1. That is precisely what I showed you here. So this is the state transition relation, the state transition function which is driving G2, and this is the one for G1. Now if I unfold the state transition system one more level, what's going to show up? Again, these states are going to show up, but the variables are going to change. So now, to characterize the set of states here, I will express the formula as R1 1 implies G1 2. Note that I have changed the time annotations of the variables because now I have moved to depth 2. So what is the value of G1 2? That depends on R1 at this step. What is the value of G2 2? That depends on R2, R1 and G1 at this step. So this is what you see as the variable. So this is the unfolding of the state transition system over time. But the thing to note is this is a propositional logic formula because all these variables that you see here are simple Boolean value 0, 1 variables. So I've taken this state transition system. I've done a bounded unfolding of the state transition system to get a big propositional logic formula. On the other side, what you see here is the encoding of the property, but I'll not get into that. So this is what comes from the property. Now the crux of this talk and this work is how does the bounded model checking work? So essentially, how does it conclude that there is no counterexample up to this depth, or how does it get a counterexample at this depth? Very simply, what it does is it takes this big chunk of formula, this big Boolean formula, and feeds it to a SAT solver. So what does the SAT solver get? The SAT solver gets a big Boolean formula where this represents the initial state, but the SAT solver doesn't know that. This represents the state transition system unfolded up to this depth, and this represents the state transition system unfolded up to this depth. And this is what comes from the property that you want to verify. So essentially, this comes from the negation of the property. For the SAT solver, he doesn't know whether a model checker wants him to produce a counterexample or it wants you to give him a proof. All that it does is it checks for satisfiability of this formula. And that is where this entire story builds up. So underlying a bounded model checker is a powerful SAT solver that behind the scene is trying to consume the propositional logic formulas that a BMC engine is throwing at it. How is the BMC engine creating these formulas? By unrolling the state transition system over time and creating time annotated Boolean variables to represent the variables of the state transition system and the properties. So this is what we call the set of unrolled clauses, what you see here, and this comes from the property. Now, as you may notice here is as BMC reaches more and more depth, as it goes deeper and deeper, because you can't really be sure of the violation of a property by just looking at depth 1 or depth 2, because when the user wants to know, is there any state in the system where x is equal to 0? Which means you actually have to do a reachability, a complete reachability starting from the initial state. And that's what
Why it's the next state is governed by the previous state and the current input. So it's a not-working process. Yeah, but that is a part of the state, right? You can capture that in your variable.
Yeah, but that would be like many ABC.
No, but look at my requirement. It's not just the next state. It says that always this is going to happen. So just imagine a big piece of code where you are having multiple lines of code where you start from x equal to 0. So there are so many statements. Up to this depth, I've just looked at 2 lines of my code.
Okay.
So that's how the corresponding state transition system will look like. Right?
What is encoded inside a state? Like what all is captured in the state?
The output values at a line of your code, or maybe if you look at it in this context, what is characterized encoded in a state is how the G1, G2s vary with respect to R1, R2. But this R1, R2, remember, is coming over time. So this is a sequential circuit, right? So it's R1, R2 at T0, R1, R2 at T1, and R1, R2 at T2. So this is a very simple example. Maybe I didn't understand your question here.
What I'm saying is, there are 2 ways to say it, but one way to say it is there's only one delay here.
Right.
So I can just stop at depth 2.
Why can't I just talk to them? For this specific example, yes, but in general, no, right? You have to get to the diameter of the state transition system because I want to know, so I mean, maybe for this simple example, yes, but ideally, depending on the nature of the property, you might have to go to the diameter of the system, and you don't have an easy way to estimate the diameter of the state transition system. Indeed, if you go to the diameter, that's what you want to know, right? Because that's the longest, shortest path by which I should get a counterexample. But if I could actually do some graph theoretic techniques to estimate the diameter, then I could have done the verification problem as well. Why burden the SAT solver to do that, right? So the essential idea is till you unfold up to either the diameter or the recurrence diameter. So there are different classes of properties for which you might have to look at. You can look at lower values, but you actually have to go till that. And as you do this, sorry, you had a comment?
No, I mean, please complete the sentence. I want to ask something. But
yeah, sure. So till you do that, the number of what is observed is the set of unrolled clauses is increasing with them. So that's the simple observation that I just want to make. And I'll build on this observation. Yeah.
So the diameter you talked about was the diameter of the state graph.
Yeah, which is a big state graph. I mean, not necessarily one with 3 states. Yeah.
But to move from the circuit to the state graph, is that easy step? Like, is that
I mean, at least if you look at the current model checkers, it's kind of a push button solution. We don't even care. So you give him the code and it's assume that that's kind of a transformation that we trust.
But here, isn't it better to just do it on the fly without generating the state graph? I mean, this formula that you're writing.
Yeah, so this was a easy visualization because I just took a simple-minded sequential circuit, but in general, a complex piece of code with pointers and things like that. This visualization would be hard to get. But here, I mean, this state machine was just introduced for easier visualization.
Even there, but like. No, but you see that why generate the whole graph at all? Like, I mean, so the way I'm thinking of it in algorithm terms, this is like
this is just for visualization. I mean, the solver will not generate the graph at all. They will directly generate this formula.
Yes, that's what.
Yeah, so this is just for just for easier visualization. I got this finite state machine to see. Otherwise, this unfolding, I thought maybe this showing the states would be easier. But indeed, as you're rightly saying, that I don't really need to build this graph. I can take the code and I can build the clause, and that's precisely what the tool will do. But if you really, maybe I misunderstood this question. But if you want to do some reachability, these tools are mature enough today to give you the graph. I mean, for your understanding or comprehension. But for a model checker, indeed, you don't need to. For the kind of model checkers that we are talking about.
Right.
But having said that, I would also like to point out that there are graph-based model checkers, I mean symbolic model checkers, for example, that would actually, what they would do is they would take the graph, the finite state machine from your code, they would take some kind of an automaton from the property, and then they would do intersection to understand whether the language of runs allowed by your machine, your code, and the language of runs disallowed by the specification have an intersection. So symbolic graph-based model checkers would indeed need to do that. But bound model checkers, yes, doesn't need to build the graph. Does that answer your question, or you're still?
Yeah, I'm fine.
Okay. I mean, but I'll come back to your observation and the Markov process thing. But I mean, I'll just talk about what we saw.
So when you say that there are tools which actually can build the graph, you mean up to a certain depth, they build.
Up to a certain depth.
And are there like methods which they usually also employ that given a particular formula or specification, they can also find out to what depth you need to unfold in order to say some completeness, give some completeness guarantee. I mean,
I know theoretical results, but I'm not aware of a tool or an implementation that essentially can give you that thing.
Okay,
so it depends on the structure of the property as well.
So the K may depend on the property.
And of course, the underlying state transition system.
You said that, for example, if the K was the diameter of this state transition graph, then we would be done. That's what.
I mean, yes, but we could have been done even earlier, depending on the structure of the property. But there is no easy way by which you can just give me an estimate of the diameter. I mean, estimate is fine, sure. But then I could have what do I do with the model checking? Right. So now what we set up to do in this experience, and this was the problem statement that was given by our industry colleague, is okay, having observed the fact that the set of unrolled clauses increases with depth, and there is no easy way to estimate K. Nobody gives you K for free. So what do these tools typically do? So when you run a bound model checker on an example, what they do? So they ask you to set a timeout. They say, okay, 30 seconds. Let me hit 30 seconds, and I'll be either saying that within 30 seconds I'm able to find a counterexample, or I'll just give up saying that okay, up to 30 seconds I'm not able to find a counterexample. So typically we'll talk about a timeout bound key with which a user invokes such tools, and we'll measure the performance of a BMC engine with respect to one of two criteria. One, if it is able to get a counterexample, which means it's able to falsify the property. The way this story happens is you take the specification, you put a negation, and you negate the property. So you wanted to know whether your design, all traces of the design, all traces of your code, all traces of your FSM satisfy the property. Alternatively stated, you are looking for one trace which falsifies the property. So all traces satisfy the property, meaning one trace falsifies the property, meaning one trace which agrees with the negation of the property, because this trace falsifies the property, which means this trace of the finite state machine agrees with the negation of the property. So the way they typically cast it is they take the finite state machine and take the propositional encoding of the finite state machine and they AND it with the negation of the property. So that's the typical way this stage is set up. Now, when this ANDing essentially gives you satisfiable, so let's say at some bound K, you get from the SAT solver, he says that the set of clauses that you are invoking with is satisfiable. What does that mean? That means that up to that depth, the big formula that the SAT solver consumed could find a satisfying witness. Now, these formulas are typically in conjunctive normal form, CNF. So what does that mean? That means that you have a satisfying witness that satisfies each clause ANDed, which means that this is a satisfying witness that is a valid trace of your FSM, and it's a valid trace of the negation of the property. Therefore, you have found a bug because you have a satisfying witness which kind of is common. So that's what we'll say. Within this time of T, what is the time that the tool took to get a SAT instance? So how fast it could find a counterexample? So that is one of my performance metrics.
So when you say get a SAT instance, you mean solve the SAT instance, right?
For me, I'm just the bounded model checker. So get a counterexample. Yeah. So indeed, internally, yes, get a SAT instance. However, it may as well be the case that within 30 seconds, I'm not able to get a counterexample. So you will measure me as how much depth I could analyze. So these are the two key performance metrics with which we are going to analyze BMC engines in this story. A, if you give me a counterexample, how fast you could do it. I gave you a contract of 30 seconds. How fast could you do it? B, if you said that, okay, I did a job up to 30 seconds, I could not find a counterexample, give me some more time or I give up, then I'll ask you, okay, I gave you 30 seconds, how much depth could you unfold? Till how much depth could you solve the problem? Which means you essentially unfolded these clauses and you built these big formulas. Now, the motivation for this work was like this. So typically in the ED industry, there are many...
Wait, so when you run these tests, are there standard data?
Benchmarks, yeah. I just come to that, yeah. And this is just kind of an experience talk. I mean, I'll delve on the math possibly here and there, but this was a fascinating experience that we had working on real benchmarks with real tools. In the industry, there are many BMC engines. So there are many BMC engines which are used inside IBM and outside, and there are many BMC engines. So ABC is a tool from Berkeley. It's a very popular model checking engine, which has almost, I think, 5 or 6 BMC engines. Now, the crux, where do these BMC engines differ? They differ in the underlying SAT solver that they used. And this SAT solving has been an active area of research over so many years. Very efficient heuristics, very efficient data structures, starting from, engineering contributions to theoretical contributions. And that has kind of revolutionized the state of the art in many of the problems today. So these heuristics essentially have widely different optimization techniques. And these BMC engines that are inbuilt into these tools have different performances depending on the SAT solver that they're tying up to. Because a key crux of this BMC engine is that SAT solver. The faster the SAT solver gives you SAT, the earlier you get a counterexample. The better the SAT solver is able to handle the set of clauses, you have better performance. So this is what was the observation. Now, when we looked at the popular BMC engines inside ABC, so these were these 4 BMC engines inside this ABC model checker. So what we saw is, so this is a graph which shows the time versus depth, and this is depth versus clauses. So BMC 3G, so this is time, which means you give more time, how much depth did the BMC engine reach? So what you see is after a certain point, the BMC 3G engine dominates, which means that as time increases, this goes into deeper and deeper terrains of your finite state machine. That's what is the key takeaway of here. On the other hand, what we are expecting is that since this guy is able to get into deeper and deeper and deeper into the design in the same time as others, what is the clause complexity that it is encountering? So when we look at the depth versus clause, so if you look at depth 250, which none of these guys were able to reach, this is a specific standard benchmark code. This guy encountered 4 into 10 to the power 6 kind of a clauses. Now, so BMC engines differ in their performance. The key to understand why these engines differ was the state-of-the-art technique that is used inside SAT solvers today. It's called conflict directed clause learning, or CDCL. So the engines inside ABC were having some kind of a clause learning technique that powers almost all the SAT solvers that you see here. And as the depth increases, each of these BMC engines start accumulating these conflict clauses. So what is a conflict clause? So let's say you're trying to solve a SAT instance. Now, typically standard textbook SAT solving algorithm, DPLL, all of us know what you do is you randomly take one of the variables, assign it a value 0 or 1, and then you try to see whether your clauses simplify. If your clauses simplify such that you get a unit clause, which means a single variable, remember that this is a conjunction of clauses. So if you have hit a single variable, that means you now have to assign it. Otherwise, there is no way to do that. Now, in the process of doing this unit clause resolution, so you now assign one unit clause, then you get another unit clause by simplification. And this is how things these go on. And if this process essentially gives you a witness, then you are happy. But if it does not, it may give you a conflict, which says that, oh, if you assign A equal to 0 and B equal to 1 and C equal to 0 and D equal to 1, this formula can never be satisfied. So this is what we call a conflict clause. Why does the SAT solver keep track of these conflict clauses? Because just think of the situation that this A0, B1, C1, D1 did not give you a solution, which means for this assignment, the formula cannot be satisfied. Why don't you take this and learn it when you are examining the other part of the tree? You're making other assignments to other variables. Remember, this assignment put you into trouble. So never repeat this assignment. And that's what these SAT solvers keep on learning. Now, the way these CDCL solvers work is how these conflict clauses are managed. And what we observed is, as you go to deeper and deeper depth into the BMC run, the BMC engine slows down. What do I mean? Okay, I'll show you with an animation. As the depth increases, quite understandably, the set of accumulated clauses also increases, and the BMC engines effectively have a slowdown. To the extent, there have been multiple observations which shows that if you restart the SAT solver, just forget about all conflict clauses. Just forget about most of the conflict clauses, restart the SAT solver from scratch, and it improves performance by orders. So you compare a SAT solver running for 2 hours versus a SAT solver restarted in between. Restarts essentially means that you forget about the conflict clauses. And that has given better orders of performance. So we started looking at whether this is really a serious thing that people have observed. So we did a very nice set of interesting experiments. So what we did was we took a simple BMC engine and we ran it continuously for a duration T. T was 1/800 seconds, and these are all happening on some standard benchmarks. Versus we ran a single engine with some time partitions with restart. So what do we do? So the same BMC engine, instead of running it for 1/800 seconds fully, we run it for 100, so let's say some time T. In time T, it explores up to depth D1. Then what do? I close everything off. I shut down my computer, again restart my computer, and then I again run BMC engine E1 from D1 plus 1. So remember, BMC is sound, which means up to depth D1, it has said that there is no counter example. So if you restart from D1 plus 1, you can be sure that, okay, D1 plus 1 is a fresh start. You have not remembered anything, that's fine. But at least you know that till D1, there is no counter example at all. So this is the experiment that we did. A very simple, naive experiment. And very interestingly, what we saw is these restarts indeed give you ability to reach better depths. And a very intuitive kind of an observation, the explanation for this was when you run a BMC engine for so long, the SAT solver inside and the engine itself managing these data structures, they get drowned with too many conflict clauses. And it's after a certain point of time, the set of conflict clauses increases so much that your system starts thrashing, meaning the set of conflict clauses, the footprint of the clauses is more than what the RAM that you're using. And it starts thrashing, which essentially slows down performance. In which case, the restarts essentially give you a very interesting performance improvement. So this was the first experiment that we did. So better depth and lesser overhead with restarts and partitions. So the next one.
What is the value of this small t?
Yeah, I'll substantiate all of this. So this D is the depth that E1 reached given this small slice T. So T is a small slice out of capital T. So I'll give the, yeah.
No. So the conflict clauses are a feature of the SAT solver.
Right.
So I mean, why are you stopping the BMC engine? Like, if you just restart in the SAT solver, wouldn't that have?
So ABC was not giving us a handle to restart the SAT solver. I mean,
but you handle to restart at depth D plus 1 because that.
Sorry.
So you have to restart at depth D plus 1.
That you can do from the outside. So these experiments.
That's because you saved the previous state.
Right. Yeah. I mean, but when we do a restart, we are essentially forgetting everything. It's like a full memory.
No, but then getting back to the D plus 1 level will take time.
Right. So yeah, that's a very interesting question. So just imagine, okay, that's a very interesting observation. Okay. So getting till D plus 1 versus solving till D plus 1 is different.
Okay. So you just get to that.
Get to D plus 1. So that's just great for reaching. You accumulate the clauses and you restart here. Versus solving SAT everywhere, right?
And
so
that is much smaller compared to.
Yeah. That's much smaller. And these engines, though we did a restart, I think they do some kind of clause caching which is outside the session. I mean, that we didn't know. I mean, I'm going to.
So another question is because caching seems to be the major thing.
One of the major things, but there are many.
So with the T.
Yeah, we'll play around with T. We'll just
based on the RAM side.
Yes, it has to, but we couldn't figure out a strategy. But we played around with T. That's what I'm going to tell you next. So the first thing that, as you pointed out, the first thing that we cast is say that who gives a small T? And what is the impact of T? So we did that experiment. So we ran a single engine continuously for duration T. Now, when you run a single engine continuously for duration T, another interesting thing happens. So this small slice of time that you see here is what we call a fragmentation. What is this? So this engine could explore up to some depth till here, and this part of the time it just wasted. It could not do anything. So from this point to this point, no new depth was reached. So this 30 seconds out of this 1/800 seconds was actually wasted. So up to 1770 seconds, so depth, let's say depth 215 was fully examined by a SAT solver at time 1770 clock time, but the remaining 30 seconds there was no progress. So when the thread was terminated at 1/800 seconds, the solver still said I could examine up to depth 250, which means the 30 seconds was kind of wasted. Now, when we ran the single engine in time slots, what started happening is these time waste states started accumulating in every small t time slots. So that gave us the feeling that if you restart too frequently, these wasted time will start accumulating in every restart window, because every window it will have a small unfinished time in which it's not able to make a progress. So this was another observation. And so when we did that, so this is what we call internal time fragmentation. So if you have more time wasted, which means cumulatively you're not doing useful work for some amount of this 1/800 seconds. Now, if you have the clause complexity is increasing, plus you have smaller time slots, so finally it is more time wastage. So the slot duration also matters. It is not just what is this value of T? This value of T is a very key thing to understand whether you should do very frequent restarts or you should do very delayed restarts. That the fact that you should do restarts is clear because it is accumulating so many clauses that it is not able to go forward with. So the next thing that we did this was again very simple experiments, which finally motivated some kind of theory. Hopefully I'll be able to get to that. So what we did was we ran some very simple vanilla no-brainer experiments. Took 120-second slots each, partitioned into 15 slots, 100 seconds. Now, interestingly, what happened was each of these small slots started having fragmentation. And as you go deeper and deeper and deeper, you see the clauses are going bigger and bigger and bigger. So this fragmentation, this time wasted started increasing. Vis-a-vis, when we ran with large equal size time slots of 300 seconds each, the same phenomenon was observed. As you go deeper and deeper, the time wasted increases. And this was another interesting study that we did was we ran with variable duration and increasing time slots. So what was the motivation behind this experiment? We said that, okay, when the BMC engine, when the SAT solver is in shallower depths, the complexity of the clauses that it is solving, vis-a-vis when it's at a greater depth, the complexity of the clauses that it's solving is huge, right? Because as he rightly pointed out, even when D+1, the entire clause set still remains. It's just that I've not done the SAT solving. That gives me a quick to D+1. So the clause complexity has increased. So why not give the SAT solver more time, the BMC engine more time as you go deeper? So that was the experiment that we did. And as a
would it be like so to instrument the BMC solver to stop at a depth, like once the depth has been explored, that's when, so those are the only sort of candidate stopping times.
But how do I know the depth? At what depth do I make it stop? So
that will require instrumenting the base. So it knows that.
So that is what we wanted to synthesize. That is precisely what we wanted to get at. So again, here this was the result. So this with variable time slots was what was increasing. So what was key is we need to determine a good partition. We need to balance the time slot length, small time slots for less complex clauses versus at earlier stages and larger time slots for more complex clauses. So how do we get this value? And that was clear that all the engines performed better when they were given these increasing time slots. So how do we fix these time slots? Do we vary them geometrically? Is there some other pattern that we're missing out? Does it depend on the design? Does it not depend on the design? Is it just an architecture configuration? What essentially makes you choose these small windows such that you can harness the SAT solvers to their best performance? And the next question that we asked, and that is also one of the key things of the story, we did another experiment. What was this experiment? This experiment was with the same time partitioning. We ran the same engine E1, 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 E1 at every restart point. Remember, I started this discussion saying that I have 5 BMC engines. Versus I ran E1, E2, E3, E1, E4, E2. How I arrived at these choices is going to be unfolded in the next 5 minutes. But no surprises. What happened was these engines, shuffling between engines gave me better performance than running the same engine. So what was the key? What we observed is there are certain engines which work better at specific clause complexities. So as the design is progressing in my analysis, there are certain engines that can work at shallower depths the best. There are certain engines that work at moderate depths the best. There are certain BMC engines that work at bigger depths the best. So there is no unique BMC engine that is a solution that can give you the best at all depths. So this is the experiment that gave us the maximum success. So we were thrilled because this gave us something to look at the textbook and find out, okay, is there something that we know? So this, many of you might be wondering, this is a standard, kind of gave me the first feeling that I had is like the 101 thing that we study in reinforcement learning. There's this paradigm called Multi-Armed Bandit, here multiple arms. So you maybe for simplicity, let's think of stationary distributions. So you pull the arm, you don't know what the reward is going to get at, and we started to force fit what we have studied in the textbook into this context. And this is what happened. So this is a summary of the results that we saw. These are again on real benchmarks. I'll show you all the benchmarks. So this is part of that Harvard model checking competition. So there are standard benchmarks. Every year this competition is there. where if you can hit a depth or get a counterexample faster than the last year's champion, then you win this. So standard benchmark. So what we did on that is, this is the no partition thing. This is the depth that this engine individually reached when ran with a timeout of 1/800 seconds. And this is the corresponding time wasted. Remember, only a single engine is running, therefore this time wasted is at the end. This is partition 1, where we do 15 slots of 120 seconds, but again the single engine is running, not combined. So these 4 are single engine runs. This is partition 2, and this is this 60, 60, 120, this smaller partition at the lower class complexity and bigger partition at the higher class complexity. Now what was encouraging is this combination, the last strategy 3 that I talked about, could actually beat the single engine runs by a margin on all the benchmarks. That's what I'm going to. What was our learning? With partitioning, better depths are reached. Variable and increasing partition performs better. That's what you see here, all green. The time wasted increases for smaller partition because you now start wasting time at every small partition. So the combined BMC engine does better. It reaches more unrolling depth, and it also has less wasted time, because the fact that at this level, this is the best engine for that kind of clause complexity, the time wasted here is much lesser than the time wasted here. So this was our key observations. So we set up to solve this problem. You have a design, you have a set of engines, and you have a time bound teeth. So this is the contract which is given in that model checking competition. So every tool has to solve the problem within time t. If you can get a counterexample faster, then you are done. If you can reach better depth for uncertain instances, then you also are done. So we want to find a k-length sequence, EA1, T1, EA2, T2, such that these TIs are your restart points, such that the sum of these TIs is T. Now for 2 consecutive engines, so this EA1 and EA2 may be the same, may not be the same. So if EI stops at DI, then EA2 resumes at DI plus 1. So this is the handover, engine handover. So we needed to figure out 2 important things. A, what are going to be these TIs, the restart points? B, what is going to be the handover mechanism? So given that you stop at depth DI, while you are executing engine EI, do you hand over the control to EI back again with a restart, or you hand over the control to some EJ not equal to EI? So that was the thing that we needed to figure out. Again, as I said, this was more of observation than math. So what we did, we started looking at these RL-based multi-armed bandit things, and I mean, there are so many variants. So specifically so there is a class of these MABs which are called associative stuff. So what we realized is, it is not the case that any engine is good at any level of the design. This is a function of the depth. The goodness of an engine is a function of the depth of the design that you are analyzing. If you do a good job there, you would be able to reach greater cumulative depth. If you mess it up, meaning you give an engine which is specialized to solve the clauses towards the end, you put it up on that front, and you give this engine at the rear, then it would be a bad job. And that's what our experiments also revealed. So this was the kind of textbook translation to the problem. We thought that we have to build some kind of an exploitation stuff where initially we would explore all the engines. So we would run parallel threads, we would explore all the engines with the same timeout. We'll ask them, okay, go play it out. We'll look at this boundary and examine how much depth this guy reached, how much depth this guy reached, how much depth this guy reached, how much depth this guy reached. Assume that E3 was the one that reached the biggest depth when fielded, when allowed to play for this amount of time. We put E3 in control, and then we exploit E3 for a certain amount of time. I will quantify what this certain sum, etc. mean. And then at some point of time, I would hand over back control to the exploration phase again, and I will again examine all the engines at this depth. Finally, somebody will emerge the winner out of this exploration. I'll exploit a little with that, and this is the thing that will continue. But again, 2 things remain to be answered. A, what is going to be the time window? What is going to be the duration of this exploration slot? This exploration slot, is the exploration slot duration here going to be the same as the exploration slot duration here? How long are you going to exploit an engine? Is it going to be the same as what you exploited with? It's going to be more than that, less than that. How long are you going to give this engine a chance to go to better depths? And how is this handover control going to be managed? We started reading the, I think, Sadathan Bhatto's Reinforcement Learning 101 textbook. There are 17 pages on this MAB heuristic, and there are, of course, many others. So we started looking at all the different things, and we started implementing all the different things to see what gives us something that we are happy about. But what was very clear is the first lesson that we learned is this is not something that can be solved with the standard mechanisms. I mean, at least that's what appears in the textbook. The first key observation that we made, 5 more minutes? Yeah, sure. So the first key observation that we made was, if we have to design this handover mechanism, we have to somehow evaluate the engines, which means we have to associate a reward with what the engines are doing. And how do these rewards get assigned? Based on the clauses, the complexity of the clauses that they're solving, and the depth they are analyzing. So just think of these two situations where engine E1 starts from depth 10 and solves till depth 25 in 60 seconds. And engine E2 starts from depth 20 and solves till depth 35 in 60 seconds. So do you reward them similarly? If you do just based on, if you evaluate this at a handover point, if you evaluate this based on average time per depth, it's same 4 seconds. But see, look at engine E2. They solved a bigger challenge. It started from depth 20 where the clause complexity has already increased. So what you essentially want to do is kind of a depth-weighted reward mechanism where you want to give more credit to engine E2 simply because it has solved a more complex problem in the same time. So that was one of the key points that we wanted to give. So this should be given higher reward. The second thing that reward function that we designed is inversely proportional to the weighted average time per depth. I have not included the map here, but I mean, if you're interested, I can pass on the paper to Shivashish. Also, there was another key question that we wanted to ask is, what if the engine that you have handed over control to is not able to progress further? So you put your trust on him just because in the previous exploration round, it emerged as the winner. So the cumulative reward fund that it was accumulating for so long gave you that this is the best engine to go forward with. But at this step, suddenly it just cannot progress. It is not able to make progress. So how long do you trust him? Do you just immediately take the control away from him? Do you allow him some time? So we designed some kind of a penalty mechanism to capture this. When we did that, what we observed is after a certain depth, when you reach a certain depth, so this is a set of specific designs, these reward mechanisms started saturating. So no matter what you play around with the parameters, this reward mechanism was kind of saturating. None of the engines was clearly becoming the winner. And there we actually had to bring in something more that was needed from the SAT solver. We also needed to understand the nature of the clauses. So all this time we are just doing mathematics from outside. We are saying, okay, this much depth, starting from this much depth. So this is the weighted average that you are looking at. But finally, you also have to take care of the nature of the clauses that it is trying to analyze. And we build this entire framework of this initial phase where we do an initial exploration followed by an exploitation, and this essentially goes on. So let me not go into even more the depth, but we tried to, so on top of these reward functions, we engineered two typical MAB policies. One, of course, is the greedy choice. So whenever you are stuck at a point where you want to hand over, which one do you choose? You greedily choose whoever is the best till that point, whoever has proven its worth till that point, versus the UCB one. So what is UCB? The UCB is the upper confidence bound. So what you do here is you just not choose the one that is clearly the best, but because it may so happen that you might actually ignore the ones which you have never seen. So there are many people, if you just continue doing greedy everywhere, so you start off exploring all of them, then somebody emerges the winner. So there's that guy, if he continues to be chosen at every time, his reward is going to increase, but the others are going to remain the same. So what you also have to do is you actually have to explore the others at different depths. So that is typically the intuition behind this UCB. So we did that as well. So we played around with these reward mechanisms and these two strategies. We did play around with different series of the times. I mean, different values of the times, and what came out is a very interesting and rosy picture. The math is there in a documented as a 25-page report. I'll pass on to you. So what was the happy part of the story is On the undetermined instances, so remember these are instances on which nobody could find a counterexample. So in the hardware model checking competition, so all these, as you asked, so all these are taken from this hardware model checking competition. So you get all the benchmarks available there, and you get some tools and the last year's maximum depth that was reached. So on these benchmarks on which nobody is able to find a counterexample, the green ones essentially show that if you see 11 out of 12, we beat at least one of them, and we are always better than single engine runs. So if you compare with single engine runs, we are always better. The Super Deep, which is the tool from Berkeley, that beat us on 2 occasions, and HWMCC beat us on 1 occasion. So we tried to examine what was the nature of clause for which this partition did not work. But to tell you the truth, these time partitions, so that how much time you are going to explore and how much time you are going to exploit, is done with very little mathematics in mind. So it is based on observations, based on what we observe from SAT solvers and certain standard results on CDCL restarts that already exist from Armin Beer's group and Fabio Somenzi's group. They've already observed this phenomenon with SAT solvers. They've actually proposed many different restart mechanisms, static restart mechanisms, dynamic restart mechanisms. We tried to take help from them, and that is what we did. This was not our contribution. We just implemented them, but what was our contribution was to engineer the reward function and do this. And the rosy picture also continued on the satisfiable instances, where also we were better than both the engines on 4 out of 5 occasions. So the kind of output that our tool gives us is this. So if you give me a design, you give me a timeout, let's say 373. So this was the challenging timeout number for this design, simply because the best engine last year had encountered a timeout up to 373. So you give us this challenge, we will give you a synthesis result of what kind of BMC engines to explore. So to conclude, I'm sorry, I took a little more than I expected. So what we observed is combination of engines performs better verification. More exploration is what we get, leading to better learning at the cost of more number of time steps to get this sequence. Increasing time sequence is preferred. You cannot explore 60 seconds here and 60 seconds at a big depth of the design. If you want to explore really well which engine is working with the clauses well at that depth, you actually have to give more time as you go deeper versus shallower time as you are towards the initial state. So the next step is we want to bring in the design characteristics. If we can model the design, if we can. So all this study, what you see here, nowhere we have seen any feature of the design. We did not look at what is there inside the design. How do the clauses essentially look like? How many gates have this much fan out and all this stuff? Inside the design, we did not do. Whatever we did was from outside, based on observations and just taking 101 RL MAB from the textbook into an implementation. That was the summary of what I wanted to share with you. Thank you very much.
So the question about instrumentation is like if the engines are instrumented to say report something like the current memory usage.
They are, and that is what we use to build those time points. Yeah. So these engines essentially, if you instrument, I mean, they're already instrumented. So it's for you to get that performance statistics and I mean run some math on them and find out whether you're going to start or restart or you're going to continue.
But they can't be instrumented even more to say figure out the depth.
But the problem is the clause complexity varies from design to design. So think of, let's say, a design which is a parity generator versus a simple arbiter. The clauses that you would encounter at depth 100 for a parity generator versus this may be quite radically different.
I was thinking in terms of the time based.
So what is constant is what you pointed out is the state transition relation.
Yeah.
So if you look at it in the equation way, what is constant in this whole journey is the state transition relation, because as you unfold, what you're essentially unfolding is the equation, the next state equation, right? So the next state equation is unfolding. If you have a big design, you reach till the diameter, of course, gives you newer and newer states. But as you go in this journey, the nature of your state transition system also dictates what kind of clauses will emerge. So maybe closer towards the depth, as you go deeper and deeper, the state transition is dense, so there are too many next states from each state. Whereas in the shallow, there are, I mean, typically when we write code, I mean, you say, okay, if the user has given 0, then you go this path, and then, but as you go deeper and deeper in the code, the switch cases that you typically write, the kind of branchings that you do in the code grows. So depending on how the solver is engineering those branches at that specific depth, what is the size of the clause cache that it has stored inside? What is the frequency with which it is going to clean up itself? All these parameters are, I mean, need to be engineered to get the thing. We just touch the tip of the iceberg from outside, peeking as less as inside as possible. Then hopefully I was able to convey the result of our whatever I would say a lazy minds experiment, but motivated by the fact that the problem came from the industry and the results were of value to the industry. That's what was the interesting thing, and we could beat the model checking competition winners of last year. So that was the happy part of the story. But there is a lot of things to do and lot to learn and engineer more advanced maybe heuristics or some other learning mechanisms. Understand what kind of learning mechanisms go inside the CDCL solver, how we can improvise them so that this can reach better depths. And this is what I think is the next direction that we're going to look at.
So what strategy 1 and strategy 2?
So strategy 1 was greedy. So whenever is a handover point, choose the guy who is till now the best. UCB, also look at people who have been relatively less explored. So if you're always greedily choosing the best, then the best goes on, right? But at certain point of time, you also need to see, have I explored others enough number of times? And that's how this UCB essentially does. You have this QTA plus root over of LNT by NTA. So this NTA is number of times you've chosen action A, and the standard textbook formula.
So
yeah,
basically what it does is explode arm key times. Then your confidence is at about 1 over root t, just by the standard. So you take the one which is the best possible upper bound. So something which is not been explored has a very high sort of whatever error bar. So you treat those error bars also as your right. So things that are not been explored, therefore be explored until the error bar.
Yeah. So some as you saying, some engine that I just explored towards the initial region, then I went so deep and I've never looked back at him. So he should also be given a chance. So we just played around with these two strategies because we also tried to do the standard epsilon greedy thing. I mean, but what value of epsilon, how to tune epsilon was beyond our knowledge. But these two gave a nice formulation. The reward function had to be engineered. I mean, of course, typically whenever you apply this kind of a thing, you have to worry about 3 things: asymptotic correctness, regret optimality, and pack guarantees. So those maths are behind the scene. And because you cannot just arbitrarily say I'm doing MMB or this and that, but at least on plate, the results look promising. That was the thing to have. To get motivated to do the math. I mean, what kind of a regret optimality is this reward function achieving? And can we really say that, okay, asymptotically, I mean, we are finally giving into the best engine sequence. At least our horizon was the model checking competition and the timer that was provided. We are happy that's the happy part of the story. You had a question which I said I'll answer. I now forgot. Sorry.
I wanted to ask, so you said that the slowdown, the reason you need these slots is because eventually the conflict slots start to accumulate and that slows down. I want to understand the nature of this slowdown. Is it the case that as the number of conflict clause increases, the system gets slower, or is it the case that at some point there is a threshold that you hit and then after that it's very slow?
So this is precisely we are not able to find out. We also want to understand that is this slowdown a constant phenomenon that given any design of relatively modest size, this slowdown always happens here, or there's something that is with the clause for which this clause learning heuristics, clause caching heuristics, and clause manipulation heuristics inside the SAT solver. That is what we are trying to break. So that needs us to go inside the SAT solver, which frankly I'm not an expert in, but I'm trying to learn that. So, but there are people like Fabio Sumenzi in Colorado and Armin Bere, they actually engineer the SAT solvers. So I think we have to learn from them what goes on inside. But the ABC tool that we are using, so we are using ABC, that's the free model checker from Berkeley, and that's state of the art worldwide. And we're using Jasper from Cadence. So Jasper has its own SAT solvers inbuilt. I cannot present the results of Jasper. But Jasper has its own class of SAT solvers. With Jasper also in the BMC mode, we experience this phenomenon. With ABC, the 5 different engines that I talked about, I experience the same phenomenon. And ABC, I know that they are using CDCL, conflict-related clause learning, and they specifically, I think, use a solver called Glucose. And so Glucose has certain set of heuristics, and there's another solver called Cadical. So what is there in the heuristics? I mean, I understand that they have proven and well-tested stuff built, accumulated with knowledge over ages, but what is that needs to be engineered, understood, and brought out to be able to go bigger depths is what we're trying to fathom.
Okay.
So
Question like you are deciding on some strategy, right? You talked about the greedy strategy or
no, this greedy UCP as a standard MEP solution strategy.
What I was asking is that what is the performance if you choose the engines randomly? Like instead of following a strategy, like sometimes we try the thing that if I pick up randomly, whether the performance is similar or not. Means
it did not give us good result, because when you're doing randomly, you're not aware of what is happening there at the depth, what kind of clauses, how this engine has performed earlier. So, I mean, if you give me the enough resources, what I would have liked to do is I would have liked to do parallelization. I would like started all possible, but then I need to figure out the restart points, right? So when do I hand over to another engine? So if you just allow me to run one permutation of the engine sequences, E1, E2, E3, 45, E1, E3, 42, E5. So if you run all the permutations of the engines, then also I need to figure out when these handovers are going to happen. So random was not the solution. We also did this epsilon greedy. I mean, with certain value of epsilon, you choose the best, and with 1 minus epsilon, we choose somebody else. But that also, I mean, we could not figure out a good epsilon on which, of course, this convergence, etc., was beyond there, but the results were not promising. Here, at least we could beat, so we got more encouraged and started doing the math. So that was. So at least what we could find out in most of the strategies is regret optimality. I mean, meaning that how close or how bad in the initial stages you are with respect to the real best. So that was a little promising in this UCP with this geometric. So this times that we did also, we tried to do some geometric series. There is something in the SAT solver community called Luby series. So there's so many things. I mean, we are drowned with so many things, but what is this? Maybe there's many other things that can be worked. So this is more of, as I was telling Shivashi, more of an experience sharing of some theory we read from textbook, some problem which came from the industry and we tried to solve. You also have a question which is stopped with him. Thank you. Thanks for your time. So I look forward to your comments. I'll pass on the paper to Shivaji. And if you have any comments, anything that you think that would enrich our work, I would be happy to look forward to. Considering it is a one hour talk, I mean, I already thought that it would be finished much earlier, but it took quite long. But so I didn't keep the map, but in the reward engineering and this penalty function, everything is there in the paper. So if you're interested, I'll pass it on. Thank you. Thank you so much.